Hello, everyone. My name is Mitya Goroshevsky. I'm CEO of Gosh, and here we're going to talk about some security problems that all of us had, the recent security problems with GitHub and some blockchains related to the secure software supply chain. And we will talk about how using Gosh could prevent that, or maybe kind of mitigate that, or help mitigate that, these attacks. So as you all remember, that happened on August 3rd, that there was a major kind of hack on GitHub, on many repositories on GitHub. Later, it was discovered that these repositories were not really hacked, but mostly they were cloned and pretended to be kind of the correct repositories with the history and everything. And so some of these repositories were used by real users. And these repositories had a line of code which basically just took all the secrets on the computer and developer computer and just shoot that to the attacker server. Some of them, part of this attack was that the malicious commit was proposed as a pull request to some legitimate repositories and was accepted without really checking. And inside this, he inserted the same line of code, which took all the secrets and sent it to the server. Basically, two things happened. It didn't happen on August 3rd. It was discovered on August 3rd by some community member. It's actually, he was preparing the attack like a month or so beforehand. So like all these repositories were created and so on and so forth. And then what happened is simultaneously, like this led to some of the wallet clients on Solana blockchain be hacked this way. And a lot of secrets were leaked through that. The dependency, I think, what they used, which was hacked, wrong dependency. And again, that was a software supply chain problem, because it happened that the wallet was kind of basically built from the some of the repositories that were hacked this way. Today we have, I invited several people from Gosh and the Gosh community, because Gosh is not one company. Gosh is really a community. So we have here people from Gosh core team. We have people from Provendo, Andrei Lashin here. And we have people from Blockchain Friends, which Roman here. So, yeah. And we're going to talk about how Gosh could prevent all of these things from happening. And there are like several aspects. We will go through them. One of them is container verification. So what we're doing, how you can verify that the container has been built correctly, the signatures of the whole thing, and like the developer signatures that are attributed to the developers and to the repositories. And then how we're using decentralized autonomous organizations to ensure, or to at least help mitigate these, for example, such things where an important commit or merge into master branch could not be just a decision of one person, for example. And we're using blockchain as a tool for kind of be part of the CI/CD process that would verify that the process is correct. So I think let's start from Andrew.
Right now we have multiple points how users can access Gosh. In this case, I'm going to present Gosh Docker extension. Let me share my screen, I guess. And as you can see, there are no organizations right now. I'm not going to create it, right? And no repositories, of course. In this case, I'm going to copy this public key.
So Roman has the pub key from Andrew.
Yes, I've received Andrew's pub key, and we have test DAO in AppGosh. So now we can add Andrew to our organization. Oh, you can see we have here 2 participants, and let's add one more.
Yeah, I already have this organization. I can see it. Okay, here we have Gosh repository. Like, let's go to third one. Yes, you can see main is just one file right now. This is dev branch. We pushed pretty much all Gosh into Gosh, and we can check history. Well, you can see the wallet ID, wallet address for the person who pushed this commit. That's pretty much it.
Yeah. Well, it basically attribution to like every commit, everything you do in Gosh has a record, and this record is on the blockchain, and of course everything is signed by the developer's key. And why it is important in the context of the attack that we saw is that, like, first of all, of course, there is like immutable signatures, right? So everything, like every commit, everything is signed by the private key of a developer, which gives you an verifiable identity and attribution of everything that has been done. So it's not only because what happened with this attack is a lot of social engineering happened. Actually, you follow all the history of the commits, that the attribution in this repository goes to the original developers, despite the fact that they did not really push into that repository, right? Because you just cloned it. But people who looked at this repository, the name of this repository was very similar to the name of the original repository, and they looked at the previous commits, and they saw the original authors of the repository. So everything was attributed to them. In Gosh, it would not happen because the commit would not be signed by original. This is it. Maybe we go to the demo now.
I will show you satellite upgrade flow with Gosh. So we have a DAO sat demo. This DAO has two members. We can see them here, the public keys, contracts of user wallets. This is the first user wallet, and this is a contract of second user wallet. We will need them later. One user is logged into the Gosh web interface, and the second user is logged in through Docker extension. To be sure that they are different users here in Docker extension and here in web interface, we can look at their public keys. So we can go to the settings and see the public key of the web interface user, and the same for Docker extension settings, and there is the another public key. Okay, let's examine our repository. So go to set demo. There is set demo repository. This repository has two branches: set deploy repository branch and the main branch. The main branch is locked, and the satellites will get updates from this branch. What means locked? That no one can push to this branch without creating a proposal, and members of DAO should vote, accept or reject this proposal. Okay, the main branch now is empty, and the set deploy branch has some files. One of them is, for example, config for satellite. You can look at this. There is some settings for satellite. Now we need to put this content, these files, into the main branch to perform satellite upgrade. For that, we need to create a pull request. Let's create it. Set deploy branch into the main branch. So here we can see files are changed, the diffs and commit changes. Now we should wait for commit. While we're pushing, I'll show you two more contracts. We remember that these two are the wallets of DAO users members, and this is a contract of satellite. It was only deployed, nothing more. It has only deploy message. And this contract is an action contract. So it is only deployed to nothing else. Okay, as I told, we push into the protected branch. So we are now redirected to the DAO events where we can vote for different kind of events. And now we should wait a bit and pull request events should appear. Oh yes, it's appeared. Look at this. So we see the event details and the changes that are going to be merged into the protected branch. So now we should vote for this. Okay, vote for proposal. Press. Our DAO has 2 members, and the total supply of DAO is 200 tokens because every member has 100. And if we want the proposal to end before the end time, we should have accepted or rejected more than half tokens of the total supply. So only one user cannot complete the proposal, and we should vote with the second DAO member too. Vote for proposal by another user. Start demo organization. Events. Here you can see the scene event pull request. And vote. Now we should wait a bit for the tokens to be updated. As the proposal was accepted by SMV, oh yes, we can see that commit appeared and the files from set deploy branch appeared in the main branch. Look at the commit. Okay, everything is good. Now we should build an image from the main branch and sign it. Okay. The image will be built now and signed. Yes, it's signing. Okay, it's done. After the image was built, we can go to the containers page and wait for images list to be loaded and find here our set demo image, and here we can validate it. Let's validate. The image validation gives us assurance that this image was built from the Gosh repository and has a blockchain signature. Okay, we'll see that image validated with success. After signing, a content signature contract was created. So we were doing this from the wallet of the second user from the Docker extension, so we should look at its wallet. Now update the page, content signature contract. Let's look at this. Yes, the content signature contract was deployed and sent, and here deploy message, and this contract send a message to action contract. We can see the address to D90, and as you remember, the this tab is the contract of an action to D90, and let's update messages of this contract. We can see that this contract accepted message from the content signature contract. Let's search for it. Oh yes, this is the message, incoming message from content signature contract. Then action contract do some stuff and send message to the satellite contract. As you remember, this top is the satellite contract. And this is the satellite address, satellite contract address. Let's search for a message to the satellite contract. Let me see once again, C9C. Oh yes, so there is outgoing message from the actions contract to the satellite, C9C3. Yes, C9C3. And let's update messages of the satellite. Oh, and we can see the incoming message from the actions contract. So all flow is done for now.
Another thing that I wanted to talk about is the log, because this is one of the things that you can always check with Gosh. And we see on the screen, Roman is showing us the log of the transactions that happens in the repository contract. These are changes to repository, basically, certain changes. I won't go into details right now, but as you can see, all the transactions that happens within this repository recorded. But what is important here, not only that it's recorded and the addresses that the message was sent through and to are recorded there, and they're all signed with the keys of the repository or like commit and or the developer and so on. But also it has this time. See, like there is a log and there is a time. And this time is immutable. It's a consensus time. And the blockchain, as we wrote about that extensively, the blockchain is the only technology that enables an objective time logging. Like this time is not, it verified, it cannot be changed. And this is very important because a lot of verification that you can do for the things that has been done into the repository or changed things in the repository or containers that you built, an artifact you have put as a part of your CI/CD process, they are all there in this immutable log with the timestamp, which are not the timestamp that client put. It's an objective timestamp. If the attack that we're talking about, just that point, if you would just look, or your script would verify the commits into that repository, you would see that basically all the commits to this repositories, because it was cloned, happened just in one day, in one particular date, which is month ago or something like that, right? Which already that would just tell you that this is something wrong with this repository, correct? So it's kind of easy to verify. And of course, right now it's maybe on Gosh. I mean, the project is half a year old, so right, or you can build it yourself. It's an open source, so you can help us build these things. You can just take the log of the events on the blockchain, and you could, for example, create a view of that events that are important to you. You can put it in Grafana or something like that for your own and create your own tool. And we will actually put some Grafana codes later. So you could clone to your repository and create this kind of view on Grafana view on what happens with your container with CI/CD process and so on and so forth, taking the events from the blockchain. On Gosh, it would be, I would say, almost impossible. And almost here is just you never say 100%, right? But in this, blockchain is very good at this actually. Like the underlying blockchain technology is very solid in preventing such things. So when you put the Git on the blockchain, you're protected by the blockchain cryptography, and this is, as I said, very good protection. Last thing we wanted to talk about is we want to go deeper. Actually, we can go even deeper. And going even deeper, we have a special guest here with us, Andrei Dashin. Andrei, yeah, you can, I think you will be able to see all the bios of people in this call just somewhere under the video. So I'm not going to give the full introduction, but Andrei is a specialist in formal verification of the software code, and he's one of the unique specialists in COC, which is, verifier. The program, math prover.
It's proof assistant, actually. It's called proof assistant,
We will talk about the formal verification and how we can improve the security of CI/CD process to levels which never been done before. So, Andrew, could you please talk to us about, for example, first let's start from the Gosh itself. So the Gosh itself is a smart contracts on Gosh blockchain. They will be formally verified. They're not yet because we're making a lot of changes into them right now, but they will be formally verified. So could you tell us more about the formal verification process?
Thank you, Mitya. To verify the smart contract, you need to specify it at first thing. When it was specified and verified in more or less automated way. In our project Prevent, we use a special technique to verify smart contracts, and especially on the ecosystem of Gosh. The verification is divided in three main parts. And the first thing, as I told about before, is specification. So you write the specification in a formal way, more or less. That's the main important thing is intended to perform. And then you make some, technical stuff, and after that you can prove that any particular function works as intended, right? After that, and that is the most important thing in our approach, is that you can literally prove. Then every scenario between any function in any contracts work as intended. So that is the main process of verification. So we use to achieve that, we use a special technique and even the special language we developed to make all this possible. So we call this language Ursus, but the main thing is that writing your program in Ursus, you can verify it in a very natural way in the COC subsystem.
Thanks. So, but the outcome of that would be, it is a proof that the program has no bugs in comparison to its specification. It works exactly like it's intended, and there is simply no bugs between the implementation and the specification. Am I correct?
So the outcome of the formal verification is the pure mathematical proof that your program works exactly as it was specified. Yes.
Yeah. So the difference between that and the different review of the program code or audit of the program code is that in review and audit, you just have people who looked at the code literally and say it looks okay, probably doesn't contain bugs. You have tests that you can write, but all of this provides certain amount of coverage for the program. The only way to really prove the program doesn't have bugs in relation to its specification is formal verification. The formal verification right now used in verifying software like trains, bullet trains, and aviation industry a lot, and so stuff like that, right?
Yes, exactly. You are very right. Yeah. The main thing that you can think about formal verification is the very mission critical spheres and direction of human involvement.
But here, because guys at Provendo created this technique and the language and the tooling around the formal verification, usually to formally verify just a program, it is extremely hard, extremely expensive, extremely long process. By using programs on blockchain, and we will expand on that a little bit, you can actually contain that process and make it really, really not kind of really easy, but I would say it's much easier than the just arbitrary program using arbitrary language on arbitrary processor, right?
Yes, exactly. You know that to verify the arbitrary program scientifically impossible because of the very mathematical stuff. You know that there is a halting problem, and it is guaranteed that you cannot decide anything about program using the programs themselves. But the main thing is that if you take the particular area of development, you can specify the very effects that your program can perform, and specifying that effects, you can create some kinds of algebra that can represent the area of all outcomes of the program, and specifying them, you can verify that your program has the only outcome that you specify. And that is the main reason that we use the smart contracts at the special area for verification. Because if we take all programs in the world, there is literally impossible to imagine all the possible outcomes. You are absolutely right that having the special area like smart contracts or CI/CD scripts, we can specify all possible reasonable outcomes from them, and specifying them, we can verify that all that outcomes are possible or not possible.
But of course, it's more complicated than that, because taking just scripts in Bash, for example, you can't really verify any script in Bash or a combination of scripts running in the background of your, for example, CI/CD process, build process, right? You just cannot do that.
Yeah, we cannot do it in general. Yeah, and that is because of the very well-known problem of specification incompatibility. For some programs, you can say, we have a program A, we have specified, and we have for example, program B, we have specified also. But if we take arbitrary operator between them, some kind of composer operator, we cannot say sometimes anything about the combination, about the composition of these two programs.
Verification of one script and another doesn't provide, when they run together, you cannot verify the outcome.
Yeah, exactly. Because the verification of the composition of scripts highly depends on the execution environment.
In blockchain, we actually tackled this with the virtual machines and certain other things in the blockchain, like messages, for example. So we control the environment. And this is one of the strongest areas in the blockchain itself, is that it actually tries to control the environment. Why? Because what is like on the blockchain, every program needs to be executed not on just one machine, but on a consensus amount of machines. So you have like validating machines that exactly execute exactly the same program and need to get exactly the same result. If they won't get the same result, they won't come to the same conclusion and they won't verify the execution. So every execution on the blockchain is verified by many machines, basically. And because of that, there are certain techniques that we use in blockchain to make that work every time. Like we just discussed recently, like why blockchains don't use JVM. And the reason why they don't use JVM is that because you cannot. While repeating JVM on different machines and in just different environment, you might get different results of the program. So that won't be exactly the same. So that's why blockchains never use JVM. They use different specially created virtual machines. And one of them we're using in Gosh. When we say how we can improve the CI/CD process with the techniques of the blockchain and with the formal verification, because remember, program running on the blockchain, not only it's verifiable by repeating the operation, but it also can be formally verified as a program itself. How we can take the scripts and, for example, let's take build scripts for Docker. And how can we make this process such that it would be almost impossible to break or to insert malicious stuff inside your scripts, because the attacks on the scripts like one of the very important, not only, by the way, not only just the attacks on the scripts, but also bugs in the scripts. So what can we do? How we can, if, for example, if we have a mission critical software, again, for example, satellites or any mission critical software, deploy of this software into the containers.
The language you use to write contracts is the generic purpose language. It's Turing complete, and it is possible to write any program to represent any logic in it. So you can use just Solidity or C++ language or any language you use to create smart contracts, to create scripts for CI/CD. It's not difficult. It's more easier than to write any generic program.
But why let's say we wrote the scripts in using like async Solidity in Gosh as a smart contract. Why running smart contracts on Gosh, to verified smart contracts on Gosh would be composable and still would be formally verified?
That is because predetermined messaging system inside the blockchain of Gosh. Every contract communicates with another with the messaging system, where every message combining with another message, the order of the processing is determined. And that is a very important thing, messaging system. If we can represent our platform and like the paradigm of different stuff communicating between using the messaging, and message system is specified, then we can specify and prove of the communication.
So now you have an answer why the contracts are composable and still, contain their verification properties. So the next question I have is, okay, so we have this scripts written in async Solidity, running on Gosh, formally verified, running inside the virtual machine of Gosh. Now we want to actually build some containers of the scripts, okay? How we make this bridge? How we execute the scripts in such a way that it will actually build container inside Docker build kit, and still that this container will still be provably formally verified in terms of like the scripts that build it, the build process would be formally verified. Any ideas?
Yeah, here, for example, we can use smart contracts, for example, async Solidity, as you mentioned before. And for example, at the start, we can reproduce this specification as a graph or just JSON object or anything. We start from like empty blob or array. And in this graph, each vertex is basically a hash of an image. And if we can prove that each edge in this graph can be verifiable, and we can verify it with our smart contracts, the result will be also verifiable by induction. So basically, we can use, for example, Docker LLB, which is like great and provide us this specific graph and specification. And we basically can write our Solidity contracts, translate them to LLB, and get verifiable images pretty much.
Excellent. So like basically we take the virtual machine execution environment, we translate it into the LLB, which is an intermediate representation, right, of the build. And we know how to do that because we actually already built the LLVM compiler for Gosh, so we know how to translate C++ to, for example, contracts to IR. So we can easily port that to like LLB because it's virtually almost the same, right? And in that respect, so now we have the whole process, basically, provable process of taking the code from Gosh, writing a script in Solidity, in async Solidity, running that in TVM locally on the machine that you built because the virtual machine is run everywhere. So it's kind of provable that the execution, again, as we said, because it's repeatable. So we can prove that the execution is the same on your local machine as in the blockchain. And now we translate that to LLB, run it in the build kit, and the container we get, which means that basically the chances that you get malicious code inside scripts is very close to zero, correct? That will do that. So it's not done yet for the future development that we want to do, and Prevent the team would do that, which will enable this provable scripts, which I think never been done before. Of course, you may say, okay, I have this tons of bash scripts that I wrote, just years of work. And so what I'm doing, if I want this process, okay, so of course you take the mission critical part, the really something that you put, for example, in the space or on the train or on the plane, and so on the financial system and so on. And you just take the portions of the script, some of the basic scripts, the containers that are really mission critical, and you rewrite them, for example, in the async solidity, and then formally verify it. So you don't need to take all of the scripts that you have, for example. You can just take this, and that will be like a safe part of your process, which would be that. And we don't say that we will replace Bash anytime soon for everything, or Python for that matter. But if it's really, really important for your process, like the security, we would recommend to go through that process, and it would give you immensely more protection than just just a bash script with some code review or even audit, right? All right, guys, I think we're done for today, and hopefully you enjoyed that. The last thing I want to show you is that I have this t-shirt which I printed today. And because it's like, you see just this part, which is Gosh, I think. So I have to show you the rest. Yeah. Okay. So thanks everyone for joining. See you next time.